Okay, so today is Thursday. September 16th. Okay. All right. So what I would like to talk about today is section 3.6. Which has to do with chemical calculations using the balanced equations. Okay. And this leads us into 3.7, which is called limiting reactants. So I'll probably look at that a little bit later, but let's take a look at this here first. So we talked about balancing equations earlier in the week. And the idea is essentially that if you have reactants and reactants and products. So here's a balanced equation. Okay. That the idea of balancing is that we need to have the same amount of matter on both sides. So if you look at here, see how you've got two nitrogens? So one interpretation of this is that you have two atoms of nitrogen. And then over here, because the coefficient refers to everything that comes after it, you've also got two atoms of nitrogen here. But we can always scale that up using the mole. Remember, a mole is 6.022 times 10 to the 23rd. So this can also be interpreted as 2 moles of nitrogen, right? Now it's 1 mole of N2. Okay, so let's take a look at that. That's an important distinction. In a nitrogen N2, there are 2 nitrogen atoms, right? In one molecule, there's 2 atoms. So we can interpret this as meaning that there's 2 moles of nitrogen atoms or 1 mole of nitrogen molecules, because you're going to have half as much nitrogen as a molecule as you have as atoms because it's N2. And so the same is true over here, right? We can interpret this now as being, but look, we've got a 3 here, right? So we can interpret this as 6 atoms of hydrogen because you've got 3 of the 2's, right? 3 times 2 is 6. So this can be interpreted as 6 moles of nitrogen atoms or 3 moles of hydrogen molecules, right? This is half as much as this one because we're just counting them differently, right? So that's what we have on the reactant side. Now we go over to the product side. We've got 2 nitrogen atoms here. We've got 6 hydrogen atoms, right? Okay, so see how that is the same, right? 2 nitrogens on the left side, 2 nitrogen atoms on the right side, 6 atoms of hydrogen on the left side, 6 hydrogen atoms on the right side. And then we can also do it in terms of moles. In terms of ammonia, now we have a group, right? It's 2 moles of ammonia, right? So that's a different substance. But within that ammonia, there's nitrogen and hydrogen, okay? So we really have 2 moles of nitrogen atoms and 6 moles of hydrogen atoms. Why 6? Because we have a 2 in front of it and we have a 3 after there. So 2 times 3 is 6. So that's 6 moles of hydrogen atoms. And again, that should be the same thing we have on the left side, right? Essentially the same. Okay, so now what we're going to do is we're going to use that balanced equation to do a certain set of calculations. And typically the calculation is this. It's a very practical issue. If I have a certain amount of a reactant, how much of the other reactant do I need in order to react with it completely, right? So it'd be like this, you know, if I said, I want to make 5 cakes, how many cups of flour do I need? How many cups of sugar do I need? How many eggs do I need? There's a relationship between the ingredients in those cakes. So there's relationships between the ingredients, flour, sugar, but there's also relationships between the ingredients and the product, right? The amount of flour you put in determines how much cake you can get. In chemistry, in a chemical equation, it's more precise than that. It's more exact. So for example, in a cake, you could use a little bit less than a cup of flour and it would still be a cake. It just would be a little different, right? But that's not true in a chemical reaction. In a chemical reaction, the amount of the reactants you put in, it, because of the idea of mass conservation, it's exact. If I put in a certain amount of nitrogen, I'm going to get specifically this amount of ammonia out of it. So that's what we're going to look at here. There's a couple of different types of calculations. One involves, really it's like three. One involves mole to mole relationships. One involves mass to mole relationships. And the other one is mass to mass relationships. So I'm going to look at all three of those in this discussion. So let me, I'm just going to erase some of this here because I want to use this reaction here. Let me just clean this up a little bit. There we go. Okay, so here's our balanced equation. So here's what we'll start off with. Let's say, for example, that we have, I'm going to make the numbers nice and easy. We have 4.0. I'm going to, put some sig figs in here. 4.0 moles of nitrogen. So I'll write it under the N too. So that's how much is going into a container. So imagine it this way. Imagine you have this container. I'll make it circular here, or somewhat circular. You have this container and it has nitrogen in it. And I'm going to represent the nitrogens as little dots. So each one of those little dots is a nitrogen molecule. Now, obviously, I can't draw 4 moles of nitrogen because a mole is 6 times 10 to the 23rd. So that's a lot of dots, right? And furthermore, we have 4 moles. So even if I could draw 6 times 10 to the 23rd, I'd have to draw 4 times that. So I'm just going to draw a bunch of dots just to sort of represent that. The question now is, in this chemical equation, how much hydrogen do I need to put into that container to react with the nitrogen completely so that all of the nitrogen gets used up? So I'll represent that with red dots. So how much of this do I need to put in, right? The red dots. Well, the answer to that is pretty simple. If we look at the equation, there's a relationship. Now, even though there's no number written here, it's implied that that's a 1, right? When we don't write a number, a coefficient in front of a reactant or product, the assumption is that it's a 1. So what this tells us is that for every 3 units, I'll use the generic term unit, 3 units of hydrogen, we need 1 unit of nitrogen. It's a 1-to-3 ratio. 1-to-3, right? And so you could think of this in a sense, although this technically is not correct. You could think of it as like 1 part nitrogen, 3 parts hydrogen. So, 1 cup sugar, 3 cups flour. Now those are volumes, right? Cups are flour or volume, and we're not talking about volume specifically here. We're talking about moles, the amount. But essentially, we would say it's 1 mole of nitrogen. Oops, not neon. For every 3 moles of hydrogen. Right? It's a 1-to-3 ratio, we would say. Okay, 1 part to 3 parts. So really, if you think about it, if you have 4 moles of nitrogen, you just need 3 times as much hydrogen, right? We would just multiply it by 3. But let me be a little bit more careful about that, a little more exacting. I'm going to use the dimensional analysis in order to do this problem. So what I'm going to do is I'm going to write down the information that's given. We're given that there's 4 moles of nitrogen. Okay. And it's 3 hydrogens for every nitrogen. So I'm going to multiply that by 3 moles of hydrogen for every 1 mole of nitrogen. Okay, so I've written that as a conversion factor. And that's one of the things that we want to practice doing in here. These are exact numbers. This is not, it's not 3.1, it's not 3.0, it's exactly 3. So in terms of dimensional analysis and significant figures, this is the measurement. This one has 2 sig figs, so our answer would be limited by that one. So now take a look at the dimensional analysis. You have moles of nitrogen divided by moles of nitrogen. So that's a ratio of 1. And the only units left over are moles of hydrogen. 4 times 3 would be 12. I'm going to leave it as 2 sig figs. I'll put a decimal there. And there you go. 12, that's 2 sig figs, right? 12 dot or 12 decimal moles of hydrogen. So what that tells us is if we have 4 moles of nitrogen in there, and we want to know how much hydrogen we have to put in there to react with it completely, we have to put in 12 moles of hydrogen, 3 times as much as we put in nitrogen, okay? Now, what happens if you put less than 12 in there? Well, what'll happen is not all of the nitrogen will react. So if I were to just put, let's say 11 moles in there, then most of the nitrogen would react to form ammonia, but some of it would remain unreacted, and we call that the excess reactant, okay? In that case, the hydrogen would be a limiting reactant. We'll talk about that in section 3.7, okay? So let's take a look at another relationship here, okay? So now, what about the relationship between nitrogen and ammonia? Ammonia is the product over there, NH3. Ammonia is a common substance. We use it in cleaners, right? But it's used in all sorts of chemical materials, products, and services. There we go. Okay. So what about the relationship between nitrogen and ammonia? So here's our ammonia. Okay, well, so if I were to ask how much ammonia are you going to get out of this reaction if all of the nitrogen reacted? Well, again, we have a relationship here. The coefficient is what gives us that relationship. We have 1 part of nitrogen for every 2 parts ammonia. So it's 1 nitrogen for every 2 ammonias. And you can kind of see from a physical perspective why that's the case. You have 2 nitrogen atoms here, and you have 2 nitrogen atoms there. So it's going to be a 2-to-1 ratio. So now here's what we'll do. We'll say, okay, it's 1 to 2. So I'm going to, again, take my amount of material, 4.0 moles of nitrogen. That's what's given in the beginning, okay? And then I'm going to multiply that by this ratio. And the ratio is 2 moles of ammonia for every 1 mole of nitrogen, right? And you can see why the nitrogen's going in the denominator and ammonia is going in the numerator. We want the moles of nitrogen to cancel so that we get moles of ammonia, right? So 4 times 2 is 8, right? So 8.02 sig figs moles of ammonia. Relatively simple, right? So that tells us that if we put in 4 moles of nitrogen, we got to put in 12 moles of hydrogen. That's how much is required to react with the nitrogen. And then out of that process, we'll get 8 moles of ammonia. So notice moles are not conserved, right? So I put in 4 moles of one reactant, 12 moles of another reactant. That's a total of 16 moles, but we only ended up with 8 moles. So moles are not conserved in this in nature. It's really mass that gets conserved. And so we're going to talk about mass next. Let me show you what we can do in terms of mass. So there's our relation. Oh, before I get into mass though, I want to show you one more relationship. there's a relationship between hydrogen and ammonia as well, right? So if 12 moles of hydrogen reacts, that's going to give you a certain amount of ammonia. So let's see how much it would be. If we put in 12 moles of hydrogen, you may see this already, but I'm going to show it to you explicitly. The relationship is 2 moles of ammonia for every 3 moles of hydrogen, right? That's the relationship there. Again, it's 2 parts per 3 parts, right? So now look what happens. The moles of hydrogen cancel. You got moles of ammonia, and look what you get. 12 times 2/3, right? Think about counting by thirds, right? 4, 8, 12. So 2/3 of 12 is 8. You get exactly the same answer we got before. It's internally consistent, right? You get the same answer as we got right here. And we should, right? So the idea then is that if you know how much of one substance you have, you can figure out how much of all the other substances are either required or will be produced in this process. It's all internal to that equation. The balanced equation 1, 3, 2 in this case, that's what tells it to you. Okay, so you get the same answer. And we're going to get to mass in a moment, but I want to show you one more mole relationship. Okay, so let me do this. I'm going to show you a different balanced equation. I guess we don't need this right now, right? I'm going to show you, let's show you a different one that's not gases. Okay, let's try this one. Let's try HCl. All right, here, aqueous. So that means dissolved in water. Plus aluminum hydroxide. Let's do that one. That's a solid to form H2O, which is a liquid, and then AlCl3. So let's actually go through this one. This would be aqueous. Let's balance this equation. This one's a little different than the ones we've done before. So it's a little tricky, right? You got hydrogen in 3 of the substances here. Okay. So here's what I'll do. I'll start with, because hydrogen is distributed in 3 different things, I'm going to do it later. I'm not going to do it first. Chlorine, on the other hand, is pretty simple, right? You just have it in 1 reactant, 1 product. So let's do chlorine first. Okay. So you have 1 chlorine on the left side and 3 on the right. So I'll put a 3 in front of here. So now you have 3 chlorines on both sides. So that's pretty good. But what about aluminum? Looks like you still have 1 aluminum on both sides. Okay, that's not bad. So let's go to oxygen. What do we have in terms of oxygen? On the left side, in the aluminum hydroxide, there's 3 OHs here, right? See, there's a 3 there. So that means there's 3 oxygens. Here we've only got 1 oxygen, so I'll put a 3 there. Okay, and then let's check. Let's just make sure. We've got 3 hydrogens in the HCl. We've got 3 hydrogens in the AlOH3, right? Those parentheses. So 3 hydrogens. That's a total of 6 hydrogens. On the right side, there's 3 waters. Water is H2O, so 3 times 2 is 6. So there's 6 hydrogens on both sides. Looks pretty good, right? 3 chlorines on both sides, 1 aluminum on both sides. And so we got a balanced equation. So that looks pretty good. So now let's take a look at the numbers here. I won't go through all of them here because we've got 2 reactants and 2 products. But let's do the relationship between HCl and AlCl3. Now for this one, just to kind of drive home the point that if you know one, you can figure out all the others. let's make a number here. Now, for this one, we'll do, 0.0215 moles, right? So I'm not using such a simple number. We have a decimal number here, right? It's just a nice small number, but it's the amount of aluminum chloride that gets produced. So let's put this into words. In this reaction, 0.0215 moles of aluminum chloride are produced from the reaction of hydrochloric acid. That's the HCl. Cool stuff. Muriatic acid, they call it. And aluminum hydroxide. Okay. So how many moles of hydrochloric acid were used in this reaction? Okay, so putting it into words there, because sometimes that's a little bit more advanced idea, because part of what you're doing when you do these problems is you're practicing doing these conversions of language into calculations. So in the reaction, 0.0215 moles, I wrote that under the aluminum chloride. That's how much is produced. How many moles of hydrochloric acid had to get used to make that 0.01215 moles of aluminum chloride? Well, again, the idea is essentially these coefficients give you the relationship. You have an implied 1 there, okay? So we take the quantity or the measurement or the given. So that's how many moles of aluminum chloride were produced in the reaction. We then look and see, well, what is it they're asking? They're asking for the hydrochloric acid. That's over here. So we put that one in the top in the numerator. So 3 moles of HCl for every 1 mole of aluminum chloride. Okay, so the moles of aluminum chloride are going to cancel, and you're going to have moles of HCl. Again, the coefficients are considered exact numbers, okay? Now, in practice for cooking, those really, 3 cups could be 2.99 cups. That's not really an exact number. But in terms of a balanced equation, we assume that the coefficients are exact numbers. So if you take a look at the 0.0215, that actually has 3 significant digits, 3 significant figures. Why? Leading zeros never count for sig fig calculations. They're just placeholders. So it's just a power of 10. So that doesn't count. But the 3, the 2 and the 1 and the 5 count. So these 3 digits have 3 significant digits. Okay. So since 3 and 1 are exact numbers, our answer should have 3 significant digits. So that's pretty simple. Multiply it by 3 and you get 0.0, what is that, 645 moles of AlCl3. Okay, and there's your moles of aluminum chloride. So there's our answer, right? That's how much is required. I'm sorry, HCl. That's how much the HCl is required. Right, dimensional analysis. HCl is what we're left with. So this is the requirement in this reaction. Now in practice, you would actually need a little more than that, because if you've ever done any baking, there's a tiny bit of batter that's going to be left in the bowl, right? You can't get 100% of that batter over into the oven. But you might be able to get 95% of it, or not even 98% of it, depending on how careful you are. So same thing here. We might need a little more HCl than that. Just depends on the nature of the reaction, okay? And there you go. So that's the mole to mole. As I said, there's 3 sort of types of calculations here. So this is really number 1, which we'll call mole to mole. because what we're doing is we're taking a given amount of moles of one substance and we're figuring out how many moles of another substance are in that relationship. Okay. All right, so there's a second type of calculation, and the second type of calculation is where we're given the mass of one of the substances. And then what we're going to do is we're going to convert that to moles of that substance. So I'll actually put A for substance A. We're going to convert it to moles of A. We've already learned how to do that, but we have to keep doing that for many of these types of problems. And then we're going to convert that to moles of B. Okay, so when we get to step 3, we'll just add one more step to that. Step 3 will be converting to mass of B, right? So you can kind of see the progression here. Mole to mole, then mass to mole, and then mass to mole to mass. And then that's pretty much it. And then Alex will put in some things like giving you micrograms instead of grams. You have to do a little SI conversion, prefix conversion, or kilograms or megagrams, that kind of stuff. But those are just sort of little details we'll add in there. So let's take a look. I'm going to go back to a slightly simpler equation. So let's try one where it's pretty simple stuff. So let's do this one right here. Sodium is going to react with water. This is an interesting reaction. It's a violent reaction. Sodium will actually react with water to form sodium hydroxide, which is referred to as lye. It's pretty dangerous stuff, actually. I'll put aqueous here. And then hydrogen gas. So it's actually, it can explode. This substance, when you put sodium metal into the, you won't find sodium metal, you're familiar with gold and steel and silver and copper. Those are all metals that are on the surface of the earth, or at least in the crust. You won't find sodium metal in the earth. You'll find sodium ions, which are dissolved in water, perhaps, or locked into rocks, but you won't find sodium metal. And the reason is it's so reactive toward water. The earth has a lot of water, right? It just reacts and it forms sodium hydroxide and hydrogen gas. And the hydrogen gas in oxygen can react to form water as an explosion, is burning. You can burn hydrogen and oxygen. So for that reason, this reaction is pretty vigorous. So let's balance it. It looks like there's one sodium on both sides. I like to keep the element that's all by itself. If you remember when we balanced combustion, hydrocarbon plus oxygen, we did the oxygen last. Same thing here. Elements that are all by themselves, it's nice to leave them for the end. Okay. So if we come over to the next one, we've got 2 hydrogens on, actually there's 3 hydrogens on the right side, but only 2 on the left. There's 1 sodium, there's 1 oxygen on both sides. So it looks like hydrogen's the issue here, right? We got to figure out how to balance hydrogen. So there's a couple of different ways to do that. One way would be to put a half in front of the H2, because that would make a half times 2 would give you 1, and then 1 plus 1 would give you 2. So that would work. Another way would be to say, look, we've got 3 over here, 3 hydrogens. We've only got 2 here. So you could write, okay, let's do it this way. This is the smaller number, right? You've got 2 hydrogens on the left and 3 on the right, right? There's 1 there and 2 there, so that's 3. So we want to have 3 over here. So N, whatever that coefficient is, times 2, we want that to equal to what's on the right side, which is 1 plus 2, right? Which is 3. So N times 2 is equal to 3. So divide both sides by 2, and you get N equals 3 halves. So if you put a 3 halves here, you got a balanced equation, right? You got 3. Oh, actually you don't, right? I take that back. That's a problem because we just messed up the oxygen. I'm sorry. That didn't work very well, right? So that's a problem. We have an oxygen problem here. So now we have, in fact, we even have an oxygen problem that's going to lead to a sodium problem. So that doesn't work very well. So this is called inspection. And sometimes you can kind of go through these steps and end up with something that didn't work out very well. So let's try a different method. So let's go back to one possibility, which is that we have 2 hydrogens over here, and we got 1 and 2 over here. So that's 3. Okay, so one method would be to do this. See how this is all by itself? So what I'm going to do is I'm going to ask myself a question. If I have 2 hydrogens on the left side, and on the right side I have 1 hydrogen plus n times 2, right? N times 2. Is there any way to make n a number such that we're going to have the same number on both sides? Well, if you think about it, what could you do? Algebraically, if you subtract 1 from both sides, you get 2 minus 1, right, is equal to n times 2. So 2 minus 1 is 1. And so n times 2, divide both sides by 2, and n is a half. So that means if you put a half here, that's actually going to balance the equation. So that's one way to balance the equation. So let me show it the way that would look. Okay, so if you take a look, you got 1 sodium on both sides. You got 1 oxygen on both sides. There's 2 hydrogens on the left. There's 1 here. And then a half times 2 is 1 as well. So that kind of works. That's a method you could use. Let's see if there's any other way we can do it.
Professor.
Mm-hmm.
So I know you had mentioned before about the fractions, because what I was taught in my first chemistry was that you have to give it a fraction by like multiplying by the 2.
Right. So if you want to do that, you can do that. You can then multiply everything by 2. That's fine. To be honest with you, the statement that everything, you can't have fractions is something that people commonly teach. It's just not true. It's just not true. Alex will, because it's a software program, the way the programmers have set it up is that if you put in fractions, it'll tell you you're wrong. But chemists use fractions all the time. And so when you learn that in the first course, it's just not true. I'm sorry.
Okay.
There's a relatively famous book called Lies My History Teacher Taught Me. And the same is true sometimes, less so, but there's also some truth to that in the sciences. So when people say you have to have a fraction, there's a practical reason why they want to have fractions, just so they can grade exams and stuff like that. But in fact, we use fractions all the time. Okay. So if you want to, for these problems, if you want to leave it as a fraction, that's perfectly fine. If you want to multiply everything by 2 to get rid of the fraction, right? So if I multiply everything by 2, you can do that too. There's nothing wrong with getting rid of the fractions. Okay. And so, we've gotten rid of the fractions. Now we have all these coefficients are 2, except for the H2, and that's perfectly fine too. That's a balanced equation, right? They're both balanced. Technically speaking, you could have 100 sodiums plus 100 waters gives you 100 sodium hydroxides plus 50 hydrogens. That's a balanced equation too, right? If someone says write a balanced equation, that's a balanced equation, right? Now that would be considered poor form, because having these big coefficients, 100s and 50, that's kind of like, why would you have big coefficients like that? It doesn't make sense. But it is a balanced equation, right? And so that's often taught, I disagree with
Professor, how is it that H2, the last H2, why do you not put a 2 for that one?
Because it does have to be balanced, right? So here's what happens. If you count things up, see how you have a 2 and a 2 there? So that's 4 hydrogens, 2 times 2. You got 2 here, right? And then you already have a 2 there, so that's 2 there. So 2 plus 2 is 4 on the right side. So that gives you 4. So now it's balanced, right? You have 4 on both sides.
Mhm.
If you were to put a 2 here, now you'd have 4 here, but you also have another 2 here. You have 6 on that side, right? So that's kind of what happens when you have a diatomic. Diatomic, that already counts as 2. So you have to be careful. If you put a 2 in front of it, now you got 4. So that's why there's no 2 in front of that in the balanced equation, right? So in fact, if you take a look at this equation, see these numbers are all the same. This is half as much. And the reason it's half as much is because it's H2, right? If hydrogen behaved in such a way that it was just H, then that would change the way we balance the equation, right? We get different numbers out of it. But it happens to be a diatomic, right? So sometimes people are not comfortable doing the fractions that way. So let's see if there's any other way that we can balance this equation without doing it the way I just did it. So what I'm going to do is come back over here. Let's see if there's anything we can do. Again, the issue, I mean, sodium is balanced, oxygen is balanced at the beginning anyways. The issue is hydrogen. So what some people would say in terms of balancing this is to say, look, you got 2 over here, you got 1 plus 2 over here. So if you put a 2 here, okay, that now gives you 2 plus another 2, that's 4. And then if you say, okay, if you got 4 on the right side and you put a 2 here, now you got 4 on the left side, now it's balanced. So that's a different method, right? That's a different kind of approach. What you're doing is you're saying, hey, if you've got an odd number on one side and an even on the other, it might make sense to double this one to make this side 4, knowing very well then that if you have 4, you can make this 4 pretty easily. So that'd be a different approach. Now, obviously, what that does then is it makes it 2 oxygens on both sides, but it also makes it 2 hydrogens on the right side. I'm sorry, 2 sodiums on the right side. So you put a 2 there, and that would be a different approach. So now you got 2 sodiums on both sides. That approach is, I think that's the way they taught me when I took balancing equations. It kind of confused me. So I tend not to use that method. I tend to try to use fractions because it just makes more sense to me. But that would be a different approach. You just sort of scale up one of them. So the idea is essentially you're trying to get even numbers on both sides. And so by putting a 2 here, that gives you 4. And then that allows you to put a 2 there to give you 4. And then you just wrap it up with the sodium and you got a balanced equation. And then you got the same answer, right? You have 2, 2, 2, 1. And, that's a different way to do it. Okay. To be honest with you, there's 20 different ways to balance equations. If you look at a chemical engineering book, they use a completely different approach. It's really kind of interesting how they do it. They do it with a sort of mass conservation approach. But this is called inspection, essentially. So try not to stress out too much about the balancing. Just, write them down and just play around with them a little bit. Look for patterns, right? Look for patterns as you do them. And then, if you still need help with balancing, let me know, and then we can go over a few of them. Okay. So let's take a look now. What I want to do is I'm going to actually, just because of the time issue, I'm going to go ahead and go straight to the third step, which is mass to mole to mole to mass. Okay. So let me write it this way. This is a relatively simple equation, right? There's no crazy coefficients. We don't have like a 6 in front of anything. But let's put it this way. Let's say we do the following. Let's say we have, I'm going to write it this way, 75.00, I'm going to put 4 sig figs grams of sodium metal, right? So this solid sodium is a metal, is put into a reaction chamber with, I'm going to use the term excess water. Okay, that's fine. Don't worry about the water. When it says excess water, essentially what that means is you don't have to do any calculations with the water in this case. Okay. So the question then is, how much mass of, let's do hydrogen gas will be produced? Okay. So in this particular problem, we're not given the number of moles of sodium like we were in the previous examples. We're given the number of grams. This is a mass, right? Remember, grams is mass. So it's like essentially how much does it weigh? How much does this stuff weigh? Okay. And so we're given 75 grams of sodium metal. And then we're asked, what's the mass of hydrogen gas? That's this substance here is going to be produced. So even though the terminology is a little bit different, it's essentially the same idea. If you think about what we did before, we took moles of one substance. So in this case, it's sodium, because that's what's given. We're given information about the sodium. And then we converted it to moles of the other substance, which in this case would be hydrogen, okay? The problem here is that we're not given the moles of sodium, we're given the number of grams of sodium. However, looking back to those problems from last Thursday, where we did mass to mole conversions and moles to mass conversion, that's where this comes into play. So here's the approach we take. And I'm going to show it as a little flow chart. And I would recommend, if you're not real familiar with these problems, that you just sort of copy this flow chart down and use it as sort of a template for doing these types of problems. So it's going to be 4 boxes here. I shouldn't draw that arrow so small. I'm trying to squeeze stuff in here. And here's a little flow chart. And generally, this flow chart works for most, almost all these problems, to be honest with you. There's, again, there's little details like whether it's in scientific notation, what are the prefixes that are in there. But essentially, this is the idea. And I want to talk about this flow chart for a moment. In the previous problems, what we did was we were given the moles of one substance, and then we converted that to moles of the other substance, right? So like the ammonia and the nitrogen, the ammonia and the hydrogen. This is the middle part of this flow chart. How did we do that? We used the coefficients, right? We used the coefficients to do that. So for this particular example, I'm going to write it this way. 1 mole of H2 for every 2 moles of Na, right? That's what we did. We said, hey, there's the coefficient 1, there's the coefficient 2. We multiplied the moles of the first substance by that 1/2 to get the moles of the second substance. So that's what we did earlier. The other issue then is what's going on here. We're given the mass, 75 grams. How do we find the moles of sodium? If we had the moles of sodium, we could just use this coefficient ratio. Well, we learned how to do that in section 3.4. What you do is you do a mass to mole conversion. Right? The way we did that was we divided by the molar mass. Right? That was the mass to mole conversion. You divide by the molar mass. So for this step, you divide by the molar mass of sodium. Okay? I'm going to go through it, so we'll see it in a moment, and we'll go through the dimensional analysis, but that's essentially what we learned in 3.4. And then this last step, how do you go from moles of a substance? This is not He, by the way, this is H2. How do you go from the moles of a substance to the mass of a substance? You do the opposite. You multiply by the molar mass. And again, an analogy would be like, suppose I were giving you the number of inches and I wanted to know the number of feet, you would divide by 12, right? But if I were given the number of feet and I wanted to find the number of inches, you would multiply by 12. So that's essentially what we're doing here. We're converting by either dividing by the molar mass or multiplying by the molar mass. But if we can't remember which one we do at which time, then we use the dimensional analysis to help us kind of make sure we're doing it the right way. So what do? We multiply by the molar mass of the substance we're interested in, which in this case is H2, all right? So notice this is step 1, this is step 2, and this is step 3. Step 1 and 3, so this is step 1 and step 3. Those two steps are what we talked about in section 3.4, mass to mole or mole to mass. And then step 2, that's what we're talking about in this section right here, 3.6. So just so you can kind of put it into context of how we're going about that. Okay, so I'm going to erase this stuff down at the bottom, and then I'm going to go through the problem here. And I'm going to do it as individual steps, and we'll leave it at that. I'll do it as individual steps. Sometimes you can do it as a chain. I'll avoid doing that for this example. Okay. So here's what's given. We're given 75 grams of sodium. That's mass. Okay, so we're going to convert that to moles of sodium. The molar mass of sodium, it's element number 11. It's on the far left side of the periodic table in the 3rd row, right? So it's group 1A, 3rd row. Sodium is 22.99. So I'm going to divide that by the molar mass. So here's how we do it in terms of dimensional analysis. 1 mole of sodium is 22.99 grams, right? That's the molar mass, sometimes referred to as the atomic mass. That's fine if you want to use that term, if it's really the molar mass, okay? So look at the dimensional analysis. Grams of sodium divided by grams of sodium, that is going to give us moles of sodium, right? Okay, so 75 0.004 sig figs, trailing zeros count, particularly if there's a decimal point in there. So 75.00 divided by 22.99, and you get 3.26229 moles of sodium. Okay. Now, even though that number, I'm keeping an extra, I'm keeping extra sig fig there, even though that number is not, 2 or 5 or 10, it's not a counting number, it gets us to here. And if you recall a little bit earlier, 20 minutes ago, moles of one substance to moles of the other substance, in this case, sodium to hydrogen, we just use the coefficients. We do a ratio of coefficients. It's 1 mole of hydrogen for every 2 moles of sodium. So you're using the coefficients. So step 2, so this is 1. Step 2, which is here, you're going from 3.26. Again, I'm keeping a couple of extra sig figs. We don't want to keep rounding each step, because if you round each step, you end up with a rounding error. So it's 1 mole of hydrogen for every 2 moles of sodium. Okay. There you go. So I'm going to divide that by 2, right? Divide by 2. So 1.63114. That's a 4 moles of H2. Look at the dimensional analysis. Moles of sodium over moles of sodium. That's what we just did about 20 minutes ago, right? Okay. And then step 3. Now the question, let's go back to the question. How much mass of hydrogen gas is there, right? What's the mass? That would be in grams. It could be in kilograms. It could be in milligrams. It could be in micrograms. It could be in nanograms. It could be in other units of grams. but it would be in some unit of grams, right? A prefix with grams, right? So it is mass. So now how do we do that step? Again, all we're doing is we're saying, hey, we've got the moles of hydrogen. We want to convert that to mass. We want to convert it to grams. That's a mole to mass conversion. And the way we do that is by multiplying by the molar mass. Okay, so we take our 1.63114 moles of H2, and we multiply that by what's the molar mass of H2? Hydrogen is element number 1, far, it's the top element, right, on the left side. So it's group 1A, and it's row 1. It's 1.01 grams per mole. That's the molar mass. But it's H2. So H is 1.01. H2 would be 2 times that, 2.02. So we multiply it by 2.02 grams per mole. Right? It's not H, it's H2. Okay, so there's your moles of H2. So we're just going to multiply by 2.02. And you get 3.2949 grams of H2. Now let's do our rounding. Again, coefficients are exact numbers. We had 4 significant digits in the 75.00, so you'd think maybe 4. But actually, looking at it here, this number right here only has 3 sig figs. It's only got 3 there. I didn't use the full value in some periodic tables, 1.00794 for hydrogen. I used 1.01. So if that only has 3 sig figs, we got to round this to 3 sig figs. So 3.29 grams of hydrogen. Okay. Take a look at the numbers. If you, it's not very much, right? We put in 75 grams of sodium and we only got out 3 grams of hydrogen. And the reason for that, sodium weighs a lot. It's almost 23 grams per mole. And so it weighs a lot, but the hydrogen doesn't weigh very much. So most of the mass in the product side is going to go into the sodium hydroxide. This weighs a lot more than hydrogen. So you'd probably end up with 70 grams of sodium hydroxide or something like that. But in any case, there it is, 3.29. Okay, so that flow chart, that can be pretty useful. Okay, and in theory, you could use this flow chart for the previous problems too, right? Because the previous problems just said how many moles of one substance, right? So you're just using this second step right there. You might see a problem where they give you the mass of one substance and just ask you for the moles of the other substance. So if they gave you the mass of sodium, you could just go in and stop at moles of hydrogen, so you can use it for any of those types of problems. Okay. Now, I don't have much time left, but I think what I'm going to do is I'm going to try to kind of rip through a simple one real quick, just so you can see a second example. I'll do it pretty quickly, but you can always pause it and, take a look at it. Let me just put a new one here. So in this one, I won't write down the whole words and everything. I'll just put the numbers in here. So let's come back to that other one, nitrogen plus hydrogen. This is called the Haber process. It's an historically important reaction. So that's kind of going back to what we started off before. So in this particular case, what I'm going to do, let's do the relationship between hydrogen and ammonia. So suppose I say, hey, we've got 15.50 grams of this substance. How many grams of this substance are going to be produced, right? So cutting out all the words and just putting them as numbers, right? So given you got 15.50 grams of H2, how many grams of NH3 will be produced? Okay, so here's what I'm going to do. I'm going to say, look, you got grams of H2, 15.50 grams of H2. We want to know grams of ammonia. So the flow chart says, look, first what you got to do is you got to go to moles of H2. Okay, so really it's how many are there, not how much it weighs. And then you convert it to moles of ammonia. And then you convert moles of ammonia into grams of ammonia. Okay, so we start with the first step. So this is 1, 2, 3. 15.50 grams of hydrogen. Okay, that's given 4 significant digits. The molar mass of H2, we just did that. It's 2.02, right? But now we're going from grams to moles, so we divide by the molar mass. So 1 mole of H2 is 2.02 grams of H2. Okay, so there's our first step. So 15.50 over 2.02, and you get 7.6733 moles of H2. Okay, to go from moles of one substance to moles of another substance in the balanced equation, we use the ratio of the coefficients. So step 2, I'm going to write this number down again. We want ammonia, so that's 2 moles of ammonia for every 3 moles of H2. Be careful, right? It's not 2 over 1. If it were nitrogen, it would be a 1, but it's hydrogen, so it's a 3. So the moles of hydrogen cancel, just like grams of hydrogen canceled here. I forgot to mention that. And you're going to get moles of ammonia. So just multiply by 2/3. And you've got 5.1155 moles of ammonia. Okay. Then last step, how many grams? We're just going to convert this to grams. So 5.1155 moles of ammonia. Okay. How do you convert? Well, you have to know the molar mass. So let's do the molar mass of ammonia first. Nitrogen is in group 5A. It's in the second row. It's 14.01. Hydrogen, of course, is 1.01, but there's 3 hydrogens. So that's 17.04. So ammonia has a molar mass of 17.04. So again, if you're going from moles to grams, you multiply by the molar mass. And then the dimensional analysis will show you that that's correct. If you're multiplying, look what happens. The moles cancel and you get grams. Okay. So molar mass is how much it weighs, which is always going to be a number greater than 1 per 1 mole. That's how much 1 mole weighs. So the 1 is the moles, and then the number that's greater than 1 is the grams. Okay. So times 17.04, and you get 87.168 grams of ammonia, right? I'm writing that out explicitly. But again, it looks like we've only got 4 sig figs, so we're going to round this to 4. So 87, I'm going to round that up, right? 8 is 5 or greater, so that goes to a 7. Oh, technically, I think we had a 2.02 in there somewhere, right? So it really is 2.02. So I really should round it to 3 sig figs. So 87.2. I forgot about that that H2 and H3. There we go. Okay, so 87.2 would be your answer. Okay, so notice you started off with a small mass and you got a big mass because some of this nitrogen is being converted into there as well. So that 87.2 is made up of the 15.5 from here plus some of the nitrogen there as well. Okay, this can also be shown as a chain. So those of you that have, looked at these kinds of problems previously or a lot, or you're comfortable with it, I'm going to show you that real quick. It can be done as a chain. So what you do is you say, look, 15.50 grams of H2 times 1 mole of H2 over 2.02 grams of H2. And then it's 2 moles of NH3 for 3 moles of H2. And then 17.04 grams of NH3 over 1 mole of NH3. So take a look at your dimensional analysis. Grams of H2 cancel, moles of H2 cancel, moles of NH3 cancel, and you get 87.2 grams of ammonia. Okay, I know I did that really, really quickly, but you can watch it more than once if you want to. The chain is an optional method, so some people use that. That's perfectly fine if you don't. I actually prefer, in a way, to use this method down here because it's just, you know, a little more deliberate about what you're doing, right? And so this up here kind of, if I'm doing a quick calculation in the lab, I'll do that because, you know, I'm comfortable doing it, but you may not be at that stage yet where you can do that. Okay. So there you go. So that's section 3.6, and that's pretty much what the problems are. The reason I didn't go over any real exact Alex problems is because Alex was not logging me in for some reason this morning. But that's essentially the problems that you're doing, okay? And you can always look back at the previous semesters for that. What I want to do next is work on 3.7, which is the limiting reactant problem. Even though it's at the end of the chapter, being at the end of the chapter, there's a tendency to say, okay, well, we're running out of time, so let's not go over it. But what I'm going to do is the next meeting, which is on Tuesday, I'm going to go ahead and do limiting reactants 3.7, just so that we can really complete this chapter in its entirety. And that's not a section that needs to be avoided. It's an important section. Okay. So I'm going to go ahead and stop the recording here and have a great day. Stop it.